Okay, good morning, everyone. It's a great pleasure to be here talking to the young people in front of me. And yeah, we know that there has been a lot of recent excitement regarding the discovery of LIGO, of gravitational waves, exactly 100 years after Einstein predicted their existence. Let me clarify that this is a large international collaboration. So the project has been going on the last 25 years, and it involves something like 1,000 scientists from 15 countries. So it's very important to recognize this as a major international collaboration where all of us play a small role. So it's best, it's best not to overdo one's contribution. So essentially, it's most likely going to win a Nobel Prize, but certainly I'm not the one who is going to win a Nobel Prize. And people who have been working on this last 25 years, people who have founded this project, have been spending on this much more than anyone, younger people like me. So it's good to see the interest of the scientific community as well as the public, because it is really the public that is funding the science. Right? All this project has been funded by the taxpayers' money. So we should appreciate the interest of the public. So okay, I'm trying to give you a glimpse of basically something like 100 years quest of the search for gravitational waves. So before I talk about gravitational waves, it's important to mention Einstein's theory of the general relativity, which actually predicts the existence of gravitational waves. So the general theory of relativity proposed by Albert Einstein more than 100 years before is the most accurate theory of gravity available to us now. It builds upon Newton's work from 300 years before. So according to general relativity, gravity is the curvature of space-time. So any massive object, or in fact any forms of energy, basically curves the space-time around it. So it's something that is very hard to grasp, because something beyond our common sense. So, but one could make some simple analogies to sort of illustrate the phenomena, but the actual phenomena is much more dramatic and much more incomprehensible than this. So imagine an object. So imagine, we know that the space has 3 dimensions and the time has 1 dimension also. So it's very hard. You have to think in 4 dimensions, which is very difficult. So for the time being, let's imagine that the space has only 1 dimension, which is this, and the time has this other dimension like this. So, and you imagine that the space-time is sort of marked by a number of grid lines like this. So whenever a massive object sits in the space-time, it essentially curves the space-time around it. So that, for example, originally these lines which were parallel essentially become no longer parallel around this, near this vicinity of this object. So, it's something very strange, thinking of a space-time as something, a curved object. But one can actually measure this. So we can, we can use this using some simple geometrical principles. For example, we all studied Euclidean geometry in school. So one of the axioms of the Euclidean geometry is that if you draw a triangle, and if you add the angles inside the triangle, it adds up to 180 degrees, right? So this is what happens if you are far away from a massive object. The space-time is very flat. So for example, if you draw a triangle far away from this object, and if you add the angles inside the triangle, it adds up to 180 degrees. But if you draw the same triangle somewhere very close to this massive object, for example, if you draw a triangle on top of the surface of a football, and if you try to add up the angles, it will be more than 180 degrees. So the geometry of Euclid is only valid for flat spaces, which becomes not valid for curved spaces. And essentially the gravity manifests itself as a curvature of space-time, so that essentially all axioms of the Euclidean geometry becomes no longer valid. So you need to have a curved geometry, which is proposed by people like Riemann, etc., etc. Now, the existence of gravitational waves, the general theory of relativity has a number of interesting predictions, and the existence of gravitational waves is one of them. It's probably one of the most intriguing predictions of the GR. So you can make some simple, and it's possible to understand it in a very sort of simple way. It's probably not the most accurate understanding. So imagine two objects moving around each other, like a binary of stars. As I said earlier, basically the presence of a massive body will curve the space-time around it. And since this body is moving in the space-time, the space-time curvature also moves with the body, right? Now, if someone is watching from a large distance, you see that the space-time curvature is changing because of the motion of the body. But this information of the change of the space-time curvature with time cannot propagate with a speed faster than the speed of light, because according to Einstein's theory of special relativity, no information can travel with a speed faster than the speed of light. So this information takes a finite time to propagate through space. And this is called gravitational waves. So gravitational waves are freely propagating oscillations in the geometry of space-time. Or if you want to make an analogy with Newtonian theory, gravitational waves are freely propagating oscillations in the gravitational field, just like electromagnetic waves are freely propagating oscillations in the electric and magnetic fields. So even before the LIGO's discovery last year, people knew that gravitational waves did exist in nature. So this basically came out of a large amount of work, theoretical as well as observational work. So this observational evidence of gravitational waves comes from the observation of some objects called binary pulsars. A pulsar is a neutron star, is an extremely compact star, something that has a mass of the sun, but is compressed to a radius of something like 20 kilometers. So it's an extremely massive and compact and dense star. And this has very strong magnetic fields. As a result, the light from the star get collimated, beamed along certain directions, for example, like a torchlight. And these neutron stars typically rotate very fast, and which the axis of rotation is, in general, misaligned with the axis of the beaming of radiation. So imagine you have a torchlight that is spinning in space. So if you happen to be on the line of sight of the light, what you see is a pulse of radiation. So whenever the torchlight spins towards you, you get a pulse of radiation. And after some time, you miss the light, and again it's come back, etc. So you see pulses of radiation. So this is called a pulsar. And there are these even strange objects called binary pulsar, which are basically two pulsars orbiting each other, two neutron stars orbiting each other. And we are able to detect the radio pulses, the radio signals in the form of pulses, regular pulses, from at least one neutron star. So by studying these radio pulses, one can infer a lot of information of the system, such as the period of the orbit, for example. And due to this fast accelerating motion of these two objects, these systems emit gravitational waves. And the system loses energy into gravitational waves. As a result, the orbital separation becomes smaller and smaller. Now, if the orbital separation is reduced, then according to the Kepler's laws, the orbital period also should. Any physics students? If you separate, if the orbital separation decreases, what happens to the orbital period? The orbital period also decrease. The frequency increases, the orbital period decreases. So, and you can compute the expected change in the orbital period of system by simply using the Einstein's theory. And it turns out that the observed change in the orbital period of this binary pulsar over the last 30 years or so agrees with Einstein's prediction in a remarkably consistent way. So, for example, this is the horizontal axis here is the year starting from 1970s going up to 2008, and the vertical axis is the change in the location of the periastron, the point of closest approach of this to binary, because it's an eccentric orbit. So it's essentially something like a proxy of the change in the orbital period of the system. So these black dots shows the actual measured values from radio observations, and this line here is a prediction of Einstein's theory. So the observation agrees with the prediction in a remarkably well consistent way, which basically gives us a lot of confidence that gravitational waves do exist even before LIGO detected them last year, basically. So what has been going on the last 20 years is a quest for the direct detection of gravitational waves on the Earth. So this is done using a number of principles. One is using a method using laser interferometry. So this makes use of the a particular characteristic of gravitational waves, that they are tidal forces, just like tides in the earth. So for example, if you imagine something that is like a ring-shaped arrangement of point particles, it's a test masses. If a gravitational wave passes perpendicular to this board, essentially these rings get deformed in a very characteristic way. So the circular ring get deformed into ellipses. Basically one direction gets stretched and the opposite direction gets compressed at the same time. So they get essentially deformed in a very characteristic way, which is like tides in the ocean, for example. So this is so basically these interferometric detectors try to detect this particular type of deformation due to the passage of gravitational waves. So, okay, so interferometer works using a simple principle which is originally built by Michelson more than 100 years before. So you have a laser beam that is split into two by a beam splitter, and this is sent into two orthogonal directions which are reflected back using two mirrors which are at these two ends. Now, when these two reflected beams combine, it produces an interference, right, because it's light. Now, initially you can configure this interferometer in such a way that this interference happens destructively, so that basically no light gets leaked from this splitter. Now, when a gravitational wave passes through it, it stretches the space in a very characteristic way. So for example, one arm gets stretched and the other arm gets compressed at the same time. So this will, so let me try to show this once again. So this will introduce a relative change in the path length of these two arms. So one arm gets stretched and the other arm gets compressed. So this one arm, the light going through one arm take a longer time to come back, while this take a, the other arm the light from the other arm get a shorter time to come back. So this will produce a change in the interference pattern, which you can read off by using a photodetector placed at this so-called dark spot. So this is the way interferometers work. Now, this is a well-established technology. This has been, the interferometers have been around for more than 100 years now. But the experimental challenge is that these expected distortions are extremely tiny. So let me give you a sense of this. So imagine that this is the interferometer, and if you, for example, think of this as a part of a circle, essentially what happens is that when a gravitational wave passes through, one arm gets stretched like this, and the other arm gets compressed. So if you, for example, start with an interferometer of, let's say, length L, say 1 kilometer, for example, if you build a huge interferometer of 1 kilometer, so the expected change in the arm length, which is the delta L, is of the order of 10 to the minus 18 meter, 10 to the power 18 meter, which is an extremely small number, which is much smaller than an atom, which is much smaller than an atomic nucleus, which is much smaller than even a proton. So if you want to get a sense of this, this scale, so this length scale of 10 to the minus 18 meter is a factor of 1,000 smaller than a size of a proton. So this is the kind of measurement that LIGO is making, that LIGO is required to make if you want to detect gravitational waves. So these detectors are the most precise length measurement devices ever constructed by the humankind. So these LIGO detectors have been constructed over the last 20 years. So these are the two observatories in the two different locations of the United States. This is in the northwest and this is in the southeast. These are separated by 4,000 kilometers for certain reasons, which I'll describe. So these are essentially Michelson interferometers, the L-shaped interferometers with each arm size of a 4 kilometer. So each arm is 4 kilometer by 4 kilometer. And these LIGO detectors have done several sort of science data taking runs over the last 10 years, but until the last year, no detection of gravitational waves was made. And this was consistent with our expectations anyway. So what made the current detection possible is that there was an upgrade of these LIGO detectors, which improved their sensitivity by a factor of 3. So as a result, as soon as these so-called advanced LIGO detectors started operating in September, On the September 14th, of 2015, about 3:30 Indian time, these two LIGO observatories at two different locations observed a gravitational wave signal. So this signal arrived at essentially simultaneously, with a time delay of about 7 milliseconds between two detectors. They arrived on the one detector first, and after 7 milliseconds, the same signal was detected by another detector, which gives us a lot of confidence. So one interesting fact about these gravitational waves at this frequency is that these detectors operate in the frequency band of about 10 to 1000 hertz, which is basically the frequency of audio signals. So it's actually possible to convert the observed signal into sound and listen to it. So I will first show, as well as produce the sound of this observed signal. Unfortunately, I'll use my mic. So you will have to listen very carefully, because it's a very faint signal. And it's a very low frequency signal. You first barely hear a thud, just a very short, like a bass sound. But later in the video itself, the frequency is slightly changed so that you can hear it better. So the video will play it again. So first what you hear is the noise from the detector. Then you see a barely two thuds, which basically the whole signal lasted only like a small fraction of a second, like a 0.2 second. But even from this very small, short duration signal, you can extract a remarkable amount of information. That's something that is very remarkable about this gravitational observation. So this plot shows the observed signal in the interferometer. The horizontal axis is the time, and the vertical axis is the amplitude of the observed signal. This is the signal observed by the two detectors here in Hanford, and this is in Livingston, the two LIGO observatories, which are separated by 4,000 kilometers. And this is what is the prediction of how the signal should look like. So you can see that this observed signal matches with the prediction in a remarkably well. Even by eye, you can see that there is a signal in the data. But of course, our inference is not based on just by looking at the data by eye. It requires a much more complicated analysis, and that's why, for example, I told that the signal was observed in September 2015, and it took 5 months for the analysis, the collaboration, to announce the discovery. So all this 5 months was spent on making sure that this is indeed a gravitational wave signal, and nothing else can explain a trigger in the detector. So basically, this requires a large amount of supercomputing calculation to make sure that indeed what we are seeing is a gravitational wave signal, and to extract the information from the signal. So the signal is consistent with what is coming from the coalescence, the merger of two black holes from a very far away part of the universe. So what happens is that these two black holes are orbiting each other in a binary orbit, and because they lose energy into gravitational wave, they come closer and eventually collide with each other, eventually merge with each other to produce a single black hole, which essentially settles into a stationary Kerr black hole. And this is the expected signal from such a phenomena. And this is what we have observed. The horizontal axis is the time, and this shows the cartoon, just a cartoon of how this event would have looked like. There are two black holes orbiting each other. They come closer and closer. Eventually, they merge to form a single black hole. And this is the expected signal. And this is not a cartoon. This is an actual calculation of this particular signal. Now, so this is a remarkably significant event, in the sense that it is highly improbable for anything other than a gravitational wave signal to produce a trigger like this. So, in science, you can never say anything is certain. You can never say anything with 100% accuracy. You always make a probability statement. So, but the odds are so large. For example, the probability of making, this being wrong is something like 1 in 1 crore, a part in 10 to the 7. So it's an extremely confident discovery. So there's, it's practically, it can be practically taken as, 100% basically. So it has made into popular culture. So basically, so this observed signal is called a chirp, a particular signal shape. You can see that this amplitude of the signal is increasing as well as the frequency is increasing. So this is very similar. The time frequency characteristic of the signal is very similar to chirping of birds. So this is called a gravitational-wave chirp. So it's very commonly used in the literature. This is called a gravitational-wave chirp. And the New Yorker, one of the oldest magazines in the world, has drawn a cartoon of this discovery. There were the two birds are speaking to each other, and one is talking to the other bird, asking, "Was it you I heard just now, or was it two black holes colliding?" So it's an evidence that the gravitational wave discovery has made into the popular culture within a couple of days. So, but it has also some element of relevance to what I talked here, because a number of environmental noise sources, such as the seismic motion of the Earth, can produce triggers in the detector. So we have to basically make sure that this particular signal cannot be explained by any non-terrestrial noise sources. And this is what this exercise that has basically carried out over the last 5 months, and basically you sort of ruled out the possibility of anything else producing a signal that we have seen in the detector. And by looking at the shape of the observed signal, it's possible to make, basically infer the properties of a source, fairly accurately. For example, by looking at the source, looking at the signal, we have inferred that basically the signal was produced by the collision of two black holes with masses 36 times the mass of the sun, and another one which is 29 times the mass of the sun. And these two objects merged to form a single black hole, which is much more massive, which is a mass of 62 times the mass of the sun, and is rapidly rotating. It is extremely fast, fastly rotating black holes. And this is sort of, in fact, this is one of really the first direct observation of a signal from a black hole. We do have a lot of evidence that black holes exist in nature, and most of this come from the motion of observing the motion of things around the black hole, which is the motion of stars around the black hole, the motion of the accretion disk around the black hole, etc. And this is for the first time we are seeing a signal from the black hole directly. So I'll skip these more technical details. So this is a remarkably energetic event. For example, during this last fraction of a second, something like a star mass worth of mass is converted into energy, gravitational wave energy. According to Einstein's most famous formula, E equal to mc squared. So for example, if you put instead of m as 3 solar mass, which is a solar mass is I think 10 to the 30 kilograms, an extremely large number, and you have a c square, again 10 to the power 16. So this much of energy is radiated in a small fraction of the second. So if you, for example, this does not produce any light, but the power radiated in gravitational waves is basically much larger than the power radiated by all the stars in the universe put together. So if you just look at the power radiated at instant, the power radiated by the single merger is larger than the power in light radiated by all the stars in the universe put together. So this is by far the most luminous, most powerful astronomical source ever observed. So this allows us to test Einstein's theory in a remarkably different regime, which is not accessible to any astronomical observations or laboratory test. But remarkably, it turned out that the observed signal is fully consistent with the prediction of Einstein's theory. So this is sort of the last time people have been vindicating Einstein's theory once again. So, in some sense, the dream job of a scientist is to prove Einstein wrong. And people have been trying to do this for the last 100 years, and it has never been succeeded. Okay, I will try to give you a brief overview of the sources and the science that we expect from these gravitational wave observations. So, we have seen that this particular event is produced by the merger of two black holes, but this is not the only type of phenomena that can produce gravitational waves. For example, we know that the collapse of massive stars can produce a gravitational wave. So, for example, we know that in a star, the stars are basically in an equilibrium. For example, the gravity will try to push the star towards its center because of its own mass, while the pressure of the outgoing light, which is called the radiation pressure, balances this infalling of the matter due to the gravitational force. So once the stars run out of its nuclear fuel, essentially the gravity dominates and the star collapses to form a compact object, either a neutron star or a black hole. And this can produce a burst of gravitational radiation. So if this happens within our galaxy, we will be able to observe gravitational waves coming from such a collapse, the death of massive stars. And this can also produce other signals, for example, a supernova, a bright electromagnetic flash, which is called a supernova. And secondly, this newly formed compact object, basically, the collapse of star the core will collapse to a compact object, such as a black hole or a neutron star, while the envelope of the star gets pushed away by a luminous event, most of the time a luminous event called a supernova. So this newly formed compact object can be rapidly spinning. If it forms a if it forms a neutron star, it can rapidly spin, and it can produce a continuous gravitational wave, just like a pulsar, which produces a continuous radio wave, for example. So, and there are groups in the LIGO collaboration which look for gravitational waves from the spinning neutron stars. So, although the signal is extremely weak, much weaker than the signal from binary black hole, the point is that this is basically a sine wave that basically is persistent throughout the data. So, you can coherently follow the signal using an appropriate data analysis techniques to build up the signal to noise ratio by integrating the signal over a long time and potentially detect the signals. And so, last the most, among the various sources of gravitational waves, the most promising one is basically binaries of black holes or neutron stars. And basically, this is what we have detected for the first time. And these can be produced by basically several astrophysical channels. So, we know that, for example, if you look at the sky, most of the stars that we see in the sky are in binary orbits. Most of the stars are orbiting each other. So these two stars can, when they run out of their nuclear fuel, they can undergo a gravitational collapse and to form two black holes or two neutron stars. So most of the time, this violent phenomena will disrupt the binary orbit. These black holes or neutron stars will fly apart, but a small fraction of them will survive. And they form a binary of two black holes or two neutron stars, or a black hole and a neutron star. So these are the most promising sources of gravitational waves, and indeed, the first signal came from one of such objects. But we have basically observed the coalescence of one black hole, but there are large numbers of black holes colliding each other at different parts of the universe. So all you need at this point is to have an instrument that is sensitive to gravitational wave signals from large distances, and you just wait, and signals will come, and we will detect. That is how the LIGO will work in the future. So apart from all these astrophysical sources, the birth of the universe itself, which is believed to be in a big bang, can produce gravitational waves. So if we are able to detect it, basically you will be able to understand what exactly has happened during the first fractions of the second after the Big Bang. So this is in some sense this is the baby picture of the universe. And this is in some sense the holy grail of gravitational wave astronomy. This is the thing that we want to detect at the end. But it will take several years, and it requires more advanced detectors to do this measurement. Okay, so gravitational wave astronomy. So I've mentioned that this has basically opened up a new branch of observational astronomy. So, but if you want to do astronomy using this gravitational wave observations, it requires a worldwide network of gravitational wave detectors that are operating at different parts of the world. So this is based on a particular, this is necessitated by a particular property of this gravitational wave detectors. It is the fact that they are essentially sensitive to the gravitational waves coming from almost the entire sky. So this is very different from an optical telescope, which you can point to a particular location in the sky and you see this light coming from only that part of the sky, right? So you can observe a galaxy or a star just by pointing the telescope. But if you open up a gravitational wave detector, essentially it's sensitive to signals coming from almost the entire sky. So this is a good, in some sense that basically you can, just using a small number of detectors, you can cover the whole sky. You can basically detect gravitational wave signals coming from almost the entire sky. But it has a drawback also, which is that you're unable to tell the location where the signal is coming from. So if you want to locate the source on the sky, it requires multiple detectors. So you require multiple detectors, and these signals arrive with a time delay between multiple detectors because they travel with the speed of light. So they will arrive in one detector first, and after some time it will arrive in the other detectors, and so on. So by looking at the time of arrival of the signal at multiple detectors, you can triangulate the source on the sky. This is, for example, how the owls locate their prey. So they have 2 ears, and they look for basically sound signals coming from this prey. And by using the difference in the time of arrival of the signal, their 2 ears, their brain process, and that's how they locate the source in the sky, because they cannot see very well. So as a result, the accuracy with which you can localize the source depends on the baseline of the network, the distance between multiple detectors forming the network. So the larger the baseline, the larger the separation between multiple detectors, the better is the ability to localize the source in the sky. And currently there are a number of detectors that are sort of operating or are being built up in US, in the Europe, in Japan, etc. But most of them are in the northern hemisphere, for example. So if you are able to build one detector in closer to the equator, for example, in India or Australia, this will significantly improve the accuracy with which we can localize the source in the sky, and significantly improve the ability to do astronomy, ability to use these observations as a tool of astronomy. And there is such a proposal, and if you are following the press, you might have seen an announcement, a news item saying that the preliminary approval of this project to build a LIGO observatory in India has happened. Of course, we have to go very far with the final approval as well as the construction. But we hope that in the next 10 years or so, we will have a LIGO observatory in India also, a gravitational observatory operating in the Indian soil, which is working in collaboration with its international partners. Okay, so let me conclude my talk in the next 5 minutes or so by giving you a sense of what this means to the future of astronomy. So I think it's fair to say that most of the information that we have gained about the universe, most of the understanding that we have on the universe came from the observations, astronomical observations using light, different frequencies of light. So for example, this includes our familiar visible light, the optical light. So this is how for example, our galaxy looks like in an optical telescope. You use a large optical telescope and combine all the images. This is how our galaxy would look like. This horizontal brighter part is the galactic disk. For example, the galaxy is basically a big disk, and we are sitting on the disk itself. So basically, if you look at the galaxy, you would see just basically a line. And that's what we are seeing in the optical telescope. But if you look at the same universe using a different frequency of the electromagnetic spectrum, for example, the microwave, you will see the signals coming from a very different epoch of the universe. So this is basically what is called the cosmic microwave background radiation. And this is the light coming from 100,000 years, 1 lakh years after the Big Bang. So this is the earliest picture of the universe, for example. And if you look at the radio frequency, it's about 21 centimeter wavelength, it provides a signal from a even different epoch of the expansion of the universe, in the evolution of the universe. So all I wanted to say is that, if you look at the universe in using different frequencies of light, you get access to very different phenomena, which you could observe using other wavelengths of astronomy. So this, essentially this is, combining these observations and producing a more complete picture of the phenomena is called multi-wavelength astronomy. But recently, astronomical observations using non-electromagnetic observations also have become possible. So this is, for example, a picture of the ultra-high energy cosmic rays observed by an observatory called Auger in Argentina. So this is, these ultra-high energy cosmic rays are highly energetic protons, with energies of 10 to the 18 electron volts. And this is, we don't know where these are coming from. There's a big puzzle. And people have various ideas, but it's not fully conclusive yet. But it basically tells you basically the baby steps of a particular branch of astronomy that has happened in the last few years. And once we have more observations and more theoretical understanding, this is basically opening us to phenomena which could not have been possibly observed using electromagnetic observations. Here is another observation by the so-called Ice Cube Observatory, which looks for extremely high energy neutrinos. This is an observatory in the Antarctica. Basically, they have drilled a lot of holes in the ice of the Antarctican ice. And basically, when these high energy neutrinos pass through the ice, they produce a particular type of light called the Cherenkov radiation. And by detecting this light, they are able to detect these high energy neutrinos as well as to locate their source in the sky. So this is how their reconstructed locations of these something like 40 neutrino observations that we have in the last few years. So again, there are ideas of what could have produced these energetic neutrinos, but it's not a fully settled problem yet. So essentially, I just wanted to give you some new branches of astronomy that are opening up, and the gravitational-wave observation is the last in this step. So this is the reconstructed location of the arrival of the location of the signal that LIGO has observed in September, where the binary black hole must have located. So the accuracy with which we can localize a source in the sky is not very good. So all we can say is that it has to be somewhere in this large annular region. So it's because we don't have, this observation is made using only 2 detectors. So if you had several detectors operating at the same time, and if all of them observe the same signal, you will be able to localize a source much more precisely on the sky. And that's how the Indian observatory is going to play an important role in the future of gravitational astronomy. So let me stop by repeating a quote from Kip Thorne, the famous theoretical physicist, and who was one of the founders of the LIGO project. So he said that with this discovery, we humans are embarking on a marvelous new quest, the quest to explore the warped side of the universe, something you could not have observed until now. So this is really a starting point of a new branch of astronomy. So let me stop here and thank you very much.
Thank you, sir. Now we move on to the interactive session. You may now ask your doubts and questions to the resource person.
Good morning, sir. So first of all, it's been a privilege to have a chance to have listened to you. So I have 2 questions. I'm not sure if they let me ask both. But one, suppose we all knew that on September 14th, a gravitational wave will pass the Earth, and we looked out for some visible changes. So I know the signals are very feeble. So somehow, if we were sensitive enough, what would we have really seen as human beings? Like, would all human beings have suddenly stretched and compressed for a second when the waves passed? Or, I mean, what would have been the visible changes?
Yeah. So if you're appropriately oriented, your height and your width would have changed by a fraction of 10 to the minus 21 meters. So, yeah, but it's very hard to observe.
Yeah, and secondly, so we've just seen the distortion in space, right? So how would we imagine the distortion in time? Because the space-time as such, it gets distorted.
Yes.
So how do we imagine a distortion in time?
So the way to imagine the distortion of time is rather hard, but what happens is that the time runs slowly and fastly. It's something very hard to grasp with, but that's what happens. Your clocks will run faster, slightly faster, over one half cycle of the wave, and slightly slower the next half cycle of the wave. But it's, again, the expected changes are of the order of 10 to the minus 21 seconds using the passage of this wave. And our best clocks can have the accuracy of 10 to the minus 15 seconds. So it's a million times smaller than the accuracy which we can measure using the best clocks in the world, using optical clocks or atomic clocks.
Then are we not able to detect those waves?
We expect to detect gravitational waves from the merger of neutron stars also. So that's something, in fact, most of the people were expecting that our first signal would be from the merger of neutron stars. So it depends on how many neutron stars in the world, in the universe, versus how many black holes in the universe. And we are basically, because the black holes are much more massive, they are most luminous in the gravitational wave emission. So as a result, we are able to see black holes at a much farther distance than the neutron stars. So we will be able to see the neutrons are happening in the vicinity of our Earth, a few hundred light years, few hundred megaparsecs, so few hundred million light years. Yes. So, but we essentially, within a few years of observation of LIGO, we hope to see mergers of neutron stars also.
You mentioned that the rate of energy emission is 3 times mass of the mass of the sun. And I think you also mentioned that the total mass of the combined black holes will be 62 times. So is this too fast energy emission?
Sorry?
The energy emission is too fast in a faster rate? 3 times the...
Yes, most of this energy emission happens during the last couple of orbits before they merge and during the merger. So it's like a 2 millisecond, a fraction of a second, like 0.1 second, something like that. So essentially the energy has been, the radiation has been happening throughout the in spiral of these black holes, but the amplitude is going very rapidly during the last stages.
You mean that their mass defect was approximately 3 times the mass of the sun? The difference in mass of the two? Okay.
Yes, yeah.
Okay.
So, but it's not quite the rest mass get converted into energy, because in general relativity the mass and energy are essentially the same. So the motion itself has energy. So in some sense, it's the sort of the binding energy of the orbit is also